All right, so this video we will be doing some example problems for refraction. If you recall from the lecture, we had the big equation for refraction. It was called Snell's Law. And what Snell's Law says is if we have light traveling through some medium, so maybe it's just light's moving through the air, or light is moving through water, or wherever it is, it hits another material. At that point, of course, two things can happen. It can either reflect off the material, like if it hits a mirror, or it can refract, which would be the light goes into the material and keeps on moving. Well, we're talking about refraction here, and so what Snell's law says is when it hits the second material, because the light changes velocity in going from one material to another. In fact, if it goes from a thin or a rare material into a more dense material, so air to water, for instance, the light will slow down. It takes longer to get through the more dense material than the more rare material. And because the light slows down, it affects the projection. It affects the direction the light travels. And the equation, which tells us exactly how that direction changes, is Snell's law. And it says n1 sine theta 1 is n2 sine theta 2, where n is the index of refraction, and the index of refraction tells you about the material. What it's actually referencing is the speed of light in that material. N is the speed of light in a vacuum divided by the speed of light in that material. So this is always going to be a number 1 or greater. N is always greater than or equal to 1 because light will never move faster than the speed of light, obviously. And what I mean by that is, of course, the speed of light in a vacuum. That's as fast as it's going to get. But when it hits another material, it slows down. So V, the velocity of light in this new material, will always be a number less than c. So c over a number less than c is always greater than 1. And every material has its own index of refraction, so we can define a material by its index of refraction. For instance, ones we should know, and let's say for air, we're going to call the air the same as vacuum for our purposes. That's 1.00, exactly 1. Because we're going to assume that light travels c, the speed of light in air. So c over c is 1. Now in water, index of refraction for water, we're going to use 1.33. And the other one we're going to use is glass. That's going to be 1.5. Like I said, all materials have their own speeds of light. And in fact, glass, there's different types of glass in existence. And so some glass is 1.52, some is 1.48, some is 1.58. Different glasses have different indices of refraction, but just for the ease of numbers for the problems we will be using, we're going to call glass 1.5. The other thing, theta, in this equation, that is the angle that, let's say, the light is traveling. And that's with respect to the normal. Okay, and if you remember what normal means, this is a mathematical term. Let's say we have, here's some water, so water down here, air up here, and we have light coming in. Here's light coming in. It's going to hit the surface of the water, and in doing so will bend or get to a new angle. So let's say it bends inwards like this. Okay. And the way the theta, the angle which describes the angle of incidence or the angle of refraction, how the light is coming in, we always measure relative to the normal line. So that's the normal. And all normal means is perpendicular. So when the light hits the surface of a pond, the surface of the pond is the surface. We draw a line perpendicular to the surface, and we measure the angle with respect to that line. So here's theta. And of course, the same down here. This is theta 2. That's theta 1. If we're going from the air to the water, all the 1 stuff is the air, all the 2 stuff is the water. Okay. So that's what we learned in our video lecture. Now we want to do some examples. So let's say we have light is incident on glass at an angle, of, let's say, 40 degrees. Calculate the angle of refraction. Now, this is a peculiarity of myself in asking these questions. This is not necessarily true all the time, and so you have to be careful who's asking the problem, where are you getting this problem from. What I will say is, when I say something like this, light is incident on glass, I'm assuming we're going from air to glass, okay? If not, I would have said something like light is traveling through water and is incident onto the surface of glass. Then you know you're going from water to glass. So if I'm not specific about one of the materials, assume it's air. So in this case, light is incident on glass. So I'm going from something to glass. So glass is number 2. What's number 1? Well, if I wasn't specific, just assume I mean air, okay? If I don't mean air, then I will specify that, no, we're not going from air to glass, we're going from water to glass, okay? So if I were to draw this, what would we have? Well, here's the surface. Glass is the second surface. Air is the first. Light is coming in. It hits the surface of the glass at an angle. This angle is 40. Remember, it's always the angle with respect to the normal. That light is going to bend, okay? Now it could either bend outwards, away from the normal, or inwards, towards the normal. How do you know which way it will bend? Well, first, you don't have to assume. You can have no idea and just do the math to get the answer. But because I'm about to draw a picture, and I want the picture to look kind of right, we can use logic, our intuition about this problem, and say, well, if we're going from air to glass, we're going from something rarefied or thin, air, to something more dense, glass. And we know that when light goes from rare to dense, the light always bends in towards the normal. So the angle gets smaller. So if I were to draw this, then I would draw it like this. It gets closer to the normal line. It bends inwards. So this angle here, that'll be our theta 2. All right? Now, like I said, if you don't know that, it doesn't matter. If you just use Snell's Law and get an answer, you'll get the right answer. But you should be able to tell, based on what you're coming from and what you're going to, if you should expect the angle to get bigger or smaller. And this is important to be able to do because you want to be able, when you calculate your answer, to check to see if it makes sense. If you don't know whether the angle should get smaller or larger, then when you get an answer, you have no idea if it's right. But if I know, because I'm going from air to glass, I'm going to something more dense, I should have a smaller angle than 40. So when I get my answer, if I get an angle of 55, I know I did something wrong because it should be less than 40. Now, how less than 40? I don't know. That's what the math will tell me. But at the very least, I can look at the answer and tell if it's definitely wrong or not. Okay. So now, what do? We use Snell's Law. N1 sine theta 1 is N2 sine theta 2. All right, we're going, my one stuff is where I'm starting. I'm starting in the air and I'm going to glass. So N1 is the index of refraction of air, which is 1. Sine theta 1, what is the angle of incidence with respect to the normal? I'm coming in at 40 degrees, so theta 1 is 40. So there's the left side. Now we look at the right. And 2, I need the index of refraction of the material I'm hitting or I'm going into. I'm going into glass, so it's 1.5. Sine theta 2, but theta 2 is the thing I'm looking for. I'm looking for the angle of refraction. So there we go. Here's my equation. Everything's a bunch of numbers except, of course, for theta 2, which is what I'm looking for. So all I have to do is plug all of this into the calculator. So I should get sine theta 2 is 1 over 1.5 sine 40. How do I calculate theta 2? Well, if it's sine of theta 2 is all of this stuff, then theta 2 must be the inverse sine of that stuff. Right? Now, be careful. Make sure your calculator, when you're doing this, is in degree mode, because we're using degrees, not radians here. But when you plug it in, you should get 25.4 degrees. Before I box it, does it make sense? Light was incident, theta 1 was 40. My angle should be less than that number because I'm going to a more dense medium. 25 is less than 40, so it may be right, it may be wrong, but at least I can't tell that it's definitely wrong. So I'll be confident and I'll go ahead and box it and say that's my answer. And there we go. A nice, easy example how to use Snell's Law to calculate a refraction problem. Now, the next one I want to do is more complicated. Let's do a problem that has multiple layers, not just 2 layers, but we'll go to 3 layers. Let's say we have something like this. Light is incident on the surface of water at an angle of 30 degrees. It then continues through the water. Where it hits glass. Calculate the the angle, of refraction in the glass. All right. So let's draw it out, because sometimes trying to read the story isn't necessarily easy to get a good picture of what's going on. But if I were to draw it, it'll be a little more visually easy to understand. So first it says light is incident on the surface of water. Okay, do I know what I'm coming from? No, it's not specified in this problem. It just says it hits the surface of water, so I can assume we're starting in air and we hit water. So, okay, here's the water. And light comes in, hits the surface of the water, and I'm told that I hit at an angle of 30 degrees. Okay, so here's air and water. It then continues through the water. Well, first of all, it's going to refract, right? It doesn't just keep going straight. I went from air to water, so I bend. Do I bend inwards towards the normal or outwards away from the normal? I'm going from air to water. Water is more dense than air, so I should bend inwards. The angle should get smaller. Okay. So my light should go, oops, sorry, something like this. Where now I have some new angle, theta 2. Okay, that's the angle of refraction in the water. However, it doesn't stop there. I'm told it keeps going through the water where all of a sudden it hits glass. So now there's a new surface. Let's make it red. Here's that. And down here is glass. And the light will go through the glass. So again, I'm going to refract. So I put a new normal line, a normal line where the light is hitting the glass. And it's going to bend there. Does it bend inwards or outwards? Well, I'm going from water to glass. Glass is more dense than water, so I should bend inwards, so the angle should get even smaller. Okay, where this angle right here, very, very small angle, we'll call theta 3, which is the angle I'm looking for. The angle of refraction in the glass is theta 3. All right, so there we go. One more thing to note is just by geometry. If you look, and I'll erase this really quick, right here, that angle of incidence that's going from glass to from water to glass, I need to know what that angle is. I know theta 2, which is the angle of refraction in the water, but I need to know what's the angle from the water to the glass. Thankfully, it's the same number, right? If we, let me take that off. If we take a line, right, between parallel lines, and this angle, and this angle must be the same as that angle. They're the same angle. That's purely geometry. So that makes this easy. I don't have to do any fanciness. I happen to know that this angle here is also theta 2. Same number. And it always is, okay? It's not a special case. Every time you have a 2-layer or 3-layer or 4-layer system, the same thing's going to happen. If you know the angle that's going through the water, that's the same as the angle of incidence from the water to the next thing. All right, so now we have our picture. Now I know what I want. What I want to calculate is this theta 3. That's what I want. Now, I believe I said this in the video lecture, but I'm going to now prove that it's true. I'm going to solve this 2 different ways. Okay? I'll solve it a naive way, where I don't know that there's a shortcut, I don't know there's a trick. I'm going to do it in the most legitimate way possible. But then afterwards, I'm going to show you that there's a shortcut to make this problem a lot faster that always works. But I want to show you both because I don't want you to think, if you're worried or something about using a shortcut because you don't want to do it incorrectly, then I don't want you to think you have to do it. You don't have to. So here's the first way. First way is I need to get to theta 3. So what I'm going to do is I'm going to use Snell's Law that says N1 sine theta 1. So I'm going from air into water. Equals N2 sine theta 2. Okay? And I'm going to do this to try to get what theta 2 is. Because if I figure out what theta 2 is, then notice going from water to glass, and the glass is what I want, all I have to do is say N2 sine theta 2 is N3 sine theta 3. Well, I already calculated what theta 2 is from the first part, which I'll show you. So I now know 2 stuff in this new equation. Now I can calculate theta 3. So that's the steps. I need theta 3. Before I could get theta 3, I need theta 2. In order to get theta 2, I use Snell's Law going from 1 to 2. All right, not too bad. 1 stuff, I'm in air, and I'm going to water. So N1 is 1. Sine of theta 1, that's 30. That's the angle going from the air to the water. Equals N2. 2 stuff is water. So that's going to be 1.33 sine theta 2, which is what I want. I need to calculate theta 2. So theta 2 will be inverse sine of 1 over 1.33 sine 30. Okay, so 1 over 1.33 times sine 30. Inverse sine of all of that business gives me 22.1 degrees. 22.8, 0.08, but I'll call it 22.1. All right, now I know theta 2. Perfect. Now I use Snell's Law again, only now I don't care about the air anymore. All the air stuff is done with. I'm in the water. So the fact that air existed before makes no difference anymore. Now all I think is, my new problem, I have light in water going to glass. The angle of incidence is this theta 2, 22.1, and I want to find theta 3. All right, no problem. N2, water, 1.33. Sine theta 2, well, theta 2 is 22.1, equals N3, glass, 1.5, times sine theta 3, which is what I want. All right, so exactly as before, only now we're going from water to glass. Theta 3, then, if you do the algebra, becomes inverse sine of 1.33 over 1.5 times sine 22.1. Okay, so 1.33 over 1.5 times sine of 22.1, and then the inverse sine of all of that gives me 19.49 degrees. And there's my answer. Along the way, I've been checking myself to make sure that everything seems to be in order. From air to water, I knew the angle should get smaller, so I went from 30 to 22. And then from water to glass, again, I'm going more dense, so the angle should get smaller. I went from 22.1 to 19.5, so it got smaller. So nothing out of the ordinary, nothing making me think, oh my God, I did something wrong. Now, what's the shortcut? The shortcut is, look at what I did. I said n1 sine theta 1 is n2 sine theta 2. And then I did a whole bunch of work to calculate this theta 2 because then I needed to say n2 sine theta 2 is n3 sine theta 3. However, look at what these two equations are saying. If we get rid of the complication and we just look at basic meaning, it says A, the first equation, equals B. N1 sine theta 1, call it A. N2 sine theta 2, that's B. And then what's the second equation say? N2 sine theta 2, that's B, same B, is equal to C. Well, if A is equal to B and B equals to C, then A and C must be equal as well. So if A and C are equal, all I have to do is say N1 sine theta 1 is N3 sine theta 3. And if I do that, what do I get? 1 sine of 30, 1.5 sine theta 3. So theta 3 is inverse sine of 1 over 1.5 sine 30. Plugging this into my calculator, 1 over 1.5 times sine 30 inverse sine, and I get 19.48, or 47 actually. Now, it's not exactly, but that's purely because when I got this number, 22.1, I rounded. It was 22.08. But doing this, there's no rounding, and so I get the exact answer. But you could see, 19.47, 19.49, it's the same answer. So this is really, really good thing to know. Given a problem on a test, if it's multiple layers like this, if all I ask for is the final angle, then you could use the shortcut. Because if A equals B, and B equals C, and C equals D, then A must be equal to D as well. So you just go from the first one to the last one. However, be careful, because especially on a test, if you're rushing because of time, be careful because I may not ask what's the final angle. I may ask for all the angles. I may ask you what's the angle of refraction in the water and what's the angle of refraction in the glass. If I did that, then you would do the blue stuff I did. Do the first part, get an answer, there's your first answer. Then do the second equation, that gives you your last answer. Okay? But that's the two methods. The full-on Snell's Law for each layer individually until you get to the final layer, or shortcut, first layer equals last layer, and skip everything in between because none of it matters, and that should be fine. Now, there is another consideration. If this is real world stuff, or you have a tricky question or a professor who wants to trick you, because things like the critical angle exist, where if you remember what critical angle was, that's when the light is going from a more dense medium to a less dense medium. If the angle is too big, bigger than the critical angle, then the light doesn't actually pass into the next layer. It reflects instead. So if I were to give a question, and I said something like, okay, we're going from air to glass, and then from glass we go to water, I can set the numbers up such that the air comes in, fine, refracts, then from glass it hits the water and refracts. However, I could set it so that this angle from glass to water, theta 2 here, is bigger than the critical angle. If I did that, then the light would not go this way. It would reflect instead. Now, am I going to do this on the test? No, at least not purposely. I may accidentally pick really bad numbers where it accidentally happens, but our purposes are not to try to get the most tricky, fancy questions. I just want you to understand how to use these equations and which equations should be used. But if you're going to go into optics in some way, whether you're going to be a doctor or you're going to do lab work or research with optics, this is something you have to worry about. So it would be negligent of me to not mention that this is possible if you have a multiple layer system, that if the angles are picked in a certain way, the light may not actually get to the last layer. For us, though, don't worry about it. I'm going to try to pick numbers where that doesn't happen, and so that means things like the shortcut could work if all I want is the final answer, and I don't want the intermediate steps. Now I'm going to do a final example, and this is exactly what I was talking about with critical angle, how to calculate the critical angle of a material. So let's say I give you the question, determine the critical angle of, let's say, honey. And of course, I need to give you, since this isn't one of the standard ones, the index of refraction of honey, we're going to say is 1.4. All right. Now, here again is the way I ask questions. I say determine the critical angle of honey. That is assuming the light is coming from or going from honey into air. Okay? Remember, critical angle problems, you're starting in that material and going to something else. So if I want the critical angle of water, I'm starting in water this time. So here I'm starting in the honey, but what am I going to? If I don't tell you in the problem, assume I'm going to air. However, I could say something like, determine the critical angle for glass if the light goes from glass to water. Then you know, okay, you're going from glass to water. If all I say is, calculate the critical angle of blah, 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 then assume you're going from blah, blah, blah into air. All right, so anyway, here's our honey. Honey down here, and air is up here. Here comes my light. It's coming in. It hits on the surface of the honey. And now I'm assuming, I'm mandating, that this angle is the critical angle. And if it is the critical angle, what happens? The light skims the surface. Anything bigger than the critical angle, it would go reflect back down into the honey. Anything less than a critical angle, it would come up into the air. But at the critical angle, it just skims the surface. What does it mean to skim the surface? That means this index of refraction in the air is 90 degrees. Right? Because if it was less than the critical angle and it went into the air, then we could calculate what this angle is here. However, it's skimming the surface, so the angle of refraction must be 90 degrees. That is the definition of critical angle. The critical angle is that angle of incidence such that the angle of refraction is 90 degrees. How do I calculate it? Thankfully, we don't need a new fancy equation. We just use Snell's Law. Again, n1 sine theta 1 is n2 sine theta 2. This time, what am I looking for? I'm going from honey to air. So 1 stuff is honey, 2 stuff is air. And 1, that's 1.4. Sine theta 1, well, I don't know what theta 1 is, but that's critical angle. That's what I want. So theta c equals. And 2, I'm going to air, so that's 1. Sine theta 2 is 90 degrees because this is the critical angle. So theta c must be the inverse sine of 1 over 1.4 times sine of 90. Well, sine of 90, that's just 1. So 1 over 1.4, inverse sine of that number, gives me 45.6 degrees. And there we go. If you're in honey and you shine a laser beam, if you shine the laser beam towards the air at 45.6 degrees or bigger, then someone outside of the honey trying to look at you will not see that laser beam come out. Because it doesn't. It completely, totally reflects internally. That's total internal reflection. At exactly 45.6, the exact critical angle, it doesn't reflect back and it doesn't go through, it skims the surface instead. But if you were to shine a laser beam at 40 degrees, a lesser angle, then the laser beam would come out of the honey and someone outside can see it. So that's critical angle. It seems like it would be a complicated question, this fancy specialized thing, but it's not, because we could just use the same exact equation for all of our problems. We don't need a new equation here. What you will see, as I said in the lecture, is you'll see in books, critical angle is inverse sine of n2 over n1. Don't memorize that. There's no reason to. It's true, but the fewer things you try to memorize, the fewer equations you try to work with, the better off you're going to be. Just remember Snell's Law for everything refraction, and you'll be fine. All you have to do is know critical angle means theta 2 is 90 degrees. That's it. So, these were some practice problems for refraction. I hope this stuff has been helpful, and until next time.